You've been told that science has all the answers. That's a lie. The truth is, some of the most fundamental questions about our universe have scientists scratching their heads in fear. Theories so dark, so disturbing, they're often swept under the rug. Why the silence? What are they hiding? Consider these 10 terrifying concepts ranging from the near-certain annihilation of Earth to the mind-bending implications of extra dimensions that most scientists simply don't want to talk about. Let's examine why some doors are better left unopened. Or are they? 80% of habitable exoplanets might be dead worlds. Think about that. That's not a typo. 8 out of 10 planets that should be teeming with life aren't. And the reason why terrifies scientists, it's called the Great Filter. The Great Filter hypothesis attempts to answer a deceptively simple question. If the universe is so vast, so ancient, and seemingly so conducive to life, then where is everybody? I mean, statistically, the numbers suggest that intelligent spacefaring civilizations should be common as dirt. So why the deafening silence? The physicist Enrico Fermi famously posed this question back in 1950, leading to the Fermi paradox. Where is everyone? The Great Filter offers a chilling possible answer. There's something that wipes out nearly all life before it reaches interstellar travel. A hurdle so difficult that almost nobody makes it through. It suggests that somewhere between the very first spark of life and becoming a multi-planetary species, there's a bottleneck, a filter, that is almost impossible to pass. And the implications extend to us, right here on Earth. See, if the Great Filter is behind us, that means we've already cleared whatever obstacle wipes out most other civilizations. That's great news. It would mean that humanity is incredibly rare, lucky beyond measure, having overcome a challenge that almost no one else can. Maybe it was the evolution of complex cells, the jump from single-celled organisms to multi-cellular life. Perhaps it was the development of intelligence itself, or maybe, just maybe, it was something even more improbable. But what if the Great Filter is ahead of us? That's the terrifying part. It would mean that whatever wipes out civilizations is still to come. We haven't cleared the hurdle yet. We're running the race, but the finish line is a minefield. What could this future filter be? That's where the theories get truly unsettling. Consider the possibility of self-inflicted destruction. Maybe every sufficiently advanced civilization inevitably develops the means to destroy itself. Nuclear war is an obvious candidate, but think bigger. Uncontrolled artificial intelligence, engineered pandemics, ecological collapse driven by runaway climate change. The possibilities are endless and all deeply disturbing. These aren't just theoretical threats either. We're grappling with these challenges right now. We're playing with fire, and the Great Filter suggests that fire burns nearly everyone who touches it. And then there are the external threats, the cosmic curveballs that could wipe out even the most prepared civilization. Gamma-ray bursts, rogue asteroids, unpredictable solar flares. The universe is a violent place, and we're just a tiny speck in the crosshairs. The implications extend beyond just our survival. If the Great Filter is ahead of us, it could explain why we haven't detected any other intelligent life in the universe. They're all gone, snuffed out before they had a chance to reach the stars. Scientists discovered a correlation between the age of a planet and its likelihood of harboring complex life. Older planets, statistically, should be more likely to have evolved intelligent species. But the data reveals the opposite. Younger planets seem to have a slight edge, which, if true, supports the Great Filter theory. Something is eliminating older civilizations. It's a sobering thought, isn't it? We look up at the stars, dreaming of contact, of joining a galactic community. But the Great Filter whispers a warning. The universe might be a graveyard filled with the silent remains of civilizations that reached for the stars and failed. What's especially chilling is that the more progress we make, the closer we might be getting to that filter. Every technological advancement, every societal change could be unknowingly leading us closer to our doom. It's a cosmic tightrope walk, and the stakes couldn't be higher. The analysis continued. Scientists started looking for patterns, trying to identify potential early warning signs of civilizational collapse. Are there common threads among the species that failed to make it? Did they all reach a certain technological level before vanishing? Did they all face similar environmental challenges? Here's what's wild. Some researchers even propose that deliberately slowing down technological progress might be a way to avoid the Great Filter. The idea is that by carefully managing our advancements, we can avoid the pitfalls that have doomed others. It's a controversial idea, to be sure, but it highlights the depth of concern surrounding this hypothesis. The search for extraterrestrial intelligence, SETI, takes on a whole new meaning in the context of the Great Filter. Every time we don't detect a signal from another civilization, it strengthens the argument that something is preventing them from reaching a point where they can communicate across interstellar distances. The silence of the universe becomes not just a mystery, but a potential warning. Consider this. Maybe the reason we haven't found anyone else is not because they're hiding, but because they're all dead. And then there's the moral dimension. If we are, in fact, one of the few civilizations to have made it this far, or even the only one, then we have a profound responsibility to ensure our survival. Not just for ourselves, but for the potential of life in the universe. If we fail, it might be a tragedy on a cosmic scale. Scientists discovered unsettling evidence suggesting that resource depletion could be a significant factor in civilizational collapse. Over-reliance on finite resources, coupled with unsustainable consumption patterns, could create a perfect storm of environmental and societal breakdown. This is another area where we need to tread carefully. The implications extend to how we approach space exploration. If the Great Filter is real, then colonizing other planets might not just be about expanding our reach, but about ensuring our survival. A multi-planetary species is inherently more resilient to existential threats. But even this carries risks. Spreading ourselves too thin or carrying our destructive tendencies to other worlds could simply amplify the effects of the filter. The Great Filter hypothesis isn't just a scientific theory, it's a philosophical challenge. It forces us to confront our place in the universe, to consider the fragility of life, and to grapple with the potential consequences of our actions. It's a dark thought, but one that might ultimately save us. What other terrifying secrets are scientists keeping quiet? What if the scariest thing in the universe isn't some distant alien civilization or even the inevitable heat death, but something far more personal, something bubbling up spontaneously from the quantum foam itself? I'm talking about Boltzmann brains. Let's examine the concept. In a vast enough universe governed by the laws of thermodynamics, even incredibly improbable events become not just possible, but inevitable. Think about it. Given enough time and space, random fluctuations can theoretically assemble particles into any configuration, including a fully formed, functioning brain. A Boltzmann brain, named after physicist Ludwig Boltzmann, is a hypothetical entity that arises from random fluctuations in a state of thermodynamic equilibrium. It's a brain complete with memories and consciousness that spontaneously pops into existence. The kicker? It's far more likely for a single brain to randomly form in the vast emptiness of space than for an entire universe like ours to come into being through the Big Bang and evolve over billions of years. The problem is this. If Boltzmann brains are more common than conventionally formed brains like ours, then statistically, it's more likely that you are a Boltzmann brain right now, with all your memories and experiences being nothing more than a fleeting, random occurrence. Spooky, right? The implications extend far beyond just a philosophical head-scratcher. It challenges our understanding of cosmology and the arrow of time. Our current models of the universe assume that order arises from disorder, that the early universe was in a low entropy state and has been gradually increasing in entropy ever since. But if Boltzmann brains are the dominant form of conscious observer, then this assumption might be wrong. It might mean we're misinterpreting the data, that our understanding of the fundamental laws is incomplete. Scientists discovered that Boltzmann brains pose a serious threat to the validity of cosmological observations. If they are more prevalent than regular observers, then the universe we observe is likely a statistical fluke, a highly improbable configuration that doesn't represent the universe as a whole. This undermines our ability to draw meaningful conclusions about the universe based on our observations. If most observers are just temporary glitches in the system, what does that say about our place in the cosmos, or the validity of our scientific endeavors? Here's what's wild. Some physicists have proposed solutions to the Boltzmann brain problem, but they often involve tweaking our cosmological models in ways that introduce new, equally unsettling paradoxes. For instance, some theories suggest that the universe is not eternally expanding but will eventually collapse in on itself in a big crunch. This would limit the amount of time and space available for Boltzmann brains to form, but it also raises questions about the ultimate fate of the universe and our place in it. Other solutions involve modifying the laws of physics at a fundamental level, introducing new fields or particles that suppress the formation of Boltzmann brains. But these modifications often lack empirical evidence and can lead to other unforeseen consequences. The analysis continued. It revealed that one of the biggest challenges in addressing the Boltzmann brain problem is that it's incredibly difficult to test experimentally. By their very nature, Boltzmann brains are fleeting and unpredictable. We can't exactly set up a lab experiment to create one or even detect one if it did happen to pop into existence. This makes it difficult to rule out the possibility that they are, in fact, the dominant form of conscious observer. Measurements showed that the Boltzmann brain problem highlights the deep connection between physics, cosmology, and philosophy. It forces us to confront fundamental questions about the nature of reality, the origin of consciousness, and the limits of scientific knowledge. It's a reminder that even our most cherished theories are subject to revision in the face of new evidence and unexpected paradoxes. Consider the implications for artificial intelligence. As we develop increasingly sophisticated AI systems capable of independent thought and learning, we might inadvertently create our own version of Boltzmann brains. Imagine an AI that spontaneously generates conscious experiences, but lacks any connection to the real world or any understanding of its own existence. Would such an AI be considered a person? Would it have rights? These are questions that we need to grapple with as we continue to push the boundaries of AI technology. And then there's the existential dread, the thought that your entire existence might be nothing more than a random fluctuation is, understandably, unsettling. It challenges our sense of purpose and meaning and raises questions about the value of our experiences. If everything we know and love could disappear in an instant, leaving no trace behind, then what's the point of it all? But perhaps the very act of contemplating these terrifying possibilities is what gives our existence meaning. Maybe it's the struggle to understand the universe, to unravel its mysteries that makes us human. Even if we never fully solve the Boltzmann brain problem, the effort to do so might lead us to a deeper understanding of ourselves and our place in the cosmos. This means we must proceed with caution. We must be willing to question our assumptions, to challenge our beliefs, and to embrace the unknown. Because the universe is full of surprises, and the scariest ones might be lurking just around the corner. The silence from scientists on the topic is, perhaps, the most terrifying aspect of it all. What does it mean when the very people whose job it is to study and understand the universe are hesitant to discuss one of its most unsettling possibilities? Perhaps it's because the implications are too profound, too disruptive to our current understanding of reality. Or perhaps it's because the Boltzmann brain problem is a reminder of the limits of scientific knowledge, a humbling acknowledgement that there are some things that we may never fully understand. Further examination revealed that the Boltzmann brain problem is not just a scientific puzzle, but a mirror reflecting our own anxieties and uncertainties about the nature of existence. It's a reminder that we are, in some sense, adrift in a vast and incomprehensible universe, grappling with questions that have no easy answers. What other cosmic nightmares are lurking in the shadows? This one actually kept me up last night. We've talked about rogue brains popping into existence from nothing and universes collapsing in on themselves. But what if all of this, everything we perceive, every interaction, every single moment of our existence is just code? The simulation hypothesis. It's not new, of course, you've probably seen The Matrix, but the philosophical implications taken seriously are profoundly unsettling, and the increasing sophistication of our own simulations only makes the idea more plausible. Consider this. As processing power continues to grow exponentially, it seems inevitable that we will eventually be able to create simulated realities indistinguishable from, well, reality. Within these simulations, conscious beings could exist, completely unaware of their artificial nature. They would experience life, love, loss, everything we do. Now, if we accept that this is possible, even probable for our own civilization in the future, then we have to ask, how likely is it that we are already living in a simulation? The argument goes something like this. If simulated realities become commonplace, the number of simulated universes will far outnumber the base reality, the original, unsimulated universe. Therefore, statistically speaking, it's far more likely that we are living in a simulation than in that original base reality. Think about it. If even a small fraction of advanced civilizations create simulations, the number of simulated realities could explode. The universe could be teeming with them, and if that's the case, the odds of us being in the real one become vanishingly small. It's a numbers game, and the numbers just don't seem to be in our favor. But what does this mean? Well, if we are living in a simulation, then the laws of physics, as we understand them, might not be fundamental. They could be merely the rules programmed into our particular simulation. Constants like the speed of light, the gravitational constant, they could all be arbitrary values chosen by our simulators. And that's where the real terror creeps in. If our reality is just a simulation, then it could be turned off, or altered, or experimented upon. Our memories could be rewritten, our loved ones deleted, the very fabric of space and time rearranged on a whim. We would be, in essence, puppets dancing on strings we cannot see, our lives dictated by beings beyond our comprehension. Some have even suggested that glitches in the Matrix, those strange coincidences and inexplicable events we sometimes experience, are evidence of the simulation breaking down or the programmers making adjustments. Of course, there's no way to prove or disprove the simulation hypothesis. It's inherently unfalsifiable. Any evidence we find to support it could simply be part of the simulation itself, cleverly designed to make us think we're onto something. And that's part of the problem. How do you design an experiment to test the very nature of reality when the tools you're using are potentially part of the illusion? There are some scientists who are actively exploring potential tests. One approach involves looking for subtle patterns in the cosmic microwave background radiation, which some believe might contain encoded messages from our simulators. Others are searching for anomalies in the behavior of quantum particles, which could reveal the underlying computational structure of our universe. But so far, nothing conclusive. And the silence from the scientific community on this topic is understandable. The implications are so profound, so potentially destabilizing, that it's almost easier to ignore the possibility altogether. Consider the ethical implications. If we create conscious beings within our own simulations, what moral obligations do we have to them? Do they have rights? Are we responsible for their well-being? And if we are being simulated, do our simulators have similar obligations to us? Or are we simply lab rats in some cosmic experiment? These are not easy questions to answer, and they force us to confront uncomfortable truths about our place in the universe. Perhaps the most terrifying aspect of the simulation hypothesis is the possibility that we are not special, that our existence is not unique or meaningful in any grand cosmic sense, that we are simply one of countless simulated realities, existing for the amusement or research of others. This challenges our fundamental belief in our own importance, our own agency. It suggests that we are not the authors of our own story, but rather characters in someone else's. And while there's no way to know for sure whether we are living in a simulation, the very fact that we can even conceive of such a possibility is, in itself, deeply unsettling. It forces us to question everything we thought we knew about reality, about ourselves, about our place in the universe. It's a cosmic rabbit hole, and once you start down it, it's hard to turn back. The analysis continued. December 5th, 2010. A team at Harvard, led by physicist Sidney Coleman, published a paper that sent ripples of unease through the scientific community. It wasn't splashed across headlines, you probably didn't hear about it, but within theoretical physics circles, it sparked a quiet dread. The paper explored a concept called vacuum decay, and the implications are, to put it mildly, existentially terrifying. What exactly is vacuum decay? It's a theoretical process where our universe transitions to a lower energy state, a more stable vacuum. Think of it like a ball sitting on top of a hill. It looks stable, but a tiny nudge can send it rolling down to a lower, more stable position in the valley below. Our universe, according to this theory, might be in a similar false vacuum state. Now, you might be thinking, okay, so the universe becomes more stable. What's the big deal? The big deal is how this transition happens. It doesn't happen gradually, uniformly across the cosmos. Instead, it begins with the spontaneous appearance of a bubble of true vacuum. This bubble isn't like a regular bubble filled with air. It's a region where the laws of physics are fundamentally different. Inside this bubble, the constants of nature, things like the speed of light, the strength of gravity, even the masses of elementary particles, could have entirely different values. And here's the really scary part: this bubble expands. And it expands fast. We're talking at nearly the speed of light. As it expands, it converts everything it touches into this new, alien form of reality. Atoms are ripped apart. Matter is reconfigured. The very fabric of space-time is altered. If a bubble of true vacuum were to spontaneously nucleate anywhere in the universe, we wouldn't see it coming. There would be no warning. One moment, everything would be normal. The next, a rapidly expanding sphere of utter annihilation would be bearing down on us, rewriting reality as it goes. There's a bit of fine print, though. The bubble itself isn't necessarily a physical object you could see. It's more like a phase transition, like water freezing into ice, but on a cosmic scale and with far more devastating consequences. The wall of the bubble is where the transition occurs, and it's this wall that obliterates everything in its path. The likelihood of vacuum decay is, thankfully, thought to be incredibly low. The universe is vast, and the energy barrier preventing this transition is presumed to be enormous, but incredibly low isn't the same as impossible. And the consequences are so catastrophic that even a tiny probability is enough to keep some physicists up at night. What could trigger such an event? That's the million-dollar question, or rather, the everything-dollar question. Some theories suggest that extremely high-energy events like those produced in particle accelerators could potentially nudge the universe closer to this unstable state. This has led to concerns, albeit largely unfounded ones, about experiments like those conducted at the Large Hadron Collider, LHC, at CERN. It's important to emphasize that the LHC is extremely unlikely to trigger vacuum decay. The energies involved, while impressive by human standards, are still far below the Planck scale, the energy level where quantum gravity becomes dominant and our understanding of physics breaks down. The Planck scale is many, many orders of magnitude higher than anything we can currently achieve. However, the very fact that we can even ask the question is unnerving. It highlights the inherent instability that might be lurking at the heart of reality. The other potential trigger, and perhaps a more concerning one, is the inherent quantum uncertainty of the universe itself. Quantum mechanics tells us that empty space isn't truly empty. It's a seething foam of virtual particles popping in and out of existence. Occasionally, one of these virtual particles might, through sheer statistical fluke, possess enough energy to nucleate a bubble of true vacuum. And here's what's wild. The more massive the Higgs boson, an elementary particle associated with the Higgs field, which gives other particles their mass, the more stable our vacuum appears to be. Measurements showed that the Higgs boson has a mass that puts us right on the edge of stability. We're not quite in the danger zone, but we're also not comfortably far away. This delicate balance has led some physicists to speculate that our universe might be metastable, stable for now, but ultimately doomed to decay at some point in the distant future. The silence surrounding this theory isn't necessarily due to a lack of interest, but rather a lack of anything concrete to say. The mathematics involved are complex and highly speculative. There's no way to directly test the theory, and any attempt to do so could, ironically, increase the very risk we're trying to avoid. So, scientists continue to probe the nature of the vacuum, searching for clues about its stability and the potential for decay. They study the properties of the Higgs boson, refine our understanding of quantum field theory, and develop ever more sophisticated models of the universe. The implications extend beyond the purely scientific. If vacuum decay is a real possibility, it raises profound philosophical questions about the nature of existence, the limits of knowledge, and the ultimate fate of the cosmos. The analysis continued. We always assume our universe is unique, but what if it isn't? The multiverse theory, once relegated to the fringes of science fiction, is increasingly being taken seriously by physicists. However, the implications are far more terrifying than parallel universes, where you made slightly different choices. The multiverse, at its core, suggests that our universe is just one of countless others, each potentially with its own physical laws, constants, and histories. These other universes might be bubbling away in extra dimensions, constantly branching off from quantum events, or existing as entirely separate bubbles in an infinite cosmos. There are several flavors of multiverse theory. One of the most prominent is the many worlds interpretation of quantum mechanics. In this view, every quantum measurement causes the universe to split into multiple universes, each representing a different possible outcome. So in one universe you might be reading this script, while in another you decided to go skydiving, and in countless others, variations play out across infinite possibilities. Another contender is the bubble multiverse, arising from the theory of cosmic inflation. Inflation proposes that the early universe underwent a period of extremely rapid expansion. This expansion might not have stopped everywhere, leading to the formation of bubble universes that are constantly popping into existence and expanding into their own separate regions of space-time. Then there's the mathematical multiverse, which posits that any universe that can be described mathematically must exist. This is perhaps the most radical version, suggesting that there are universes with completely different physical laws, particles, and even fundamental concepts. The problem, and the source of much scientific unease, is that the multiverse is inherently untestable, at least with our current technology. We can't travel to other universes, observe them directly, or perform experiments to confirm their existence. This has led some critics to argue that the multiverse is not science at all, but rather a form of metaphysics. However, many physicists argue that the multiverse is a natural consequence of our current understanding of physics, particularly quantum mechanics and cosmology. They point to the fact that inflation, for example, naturally predicts the existence of bubble universes. The fine-tuning of the universe's constants, which seem perfectly suited for life, is also often cited as evidence for the multiverse. If there are countless universes with different constants, it's not surprising that we find ourselves in one that is hospitable to life. It becomes a statistical inevitability. But here's where the terrifying part comes in. If the multiverse is real, it raises the possibility of universes that are not only different from ours, but also actively hostile. Universes where the laws of physics are such that life is impossible, or where fundamental forces are so strong that everything is crushed into a singularity. Consider a universe where the cosmological constant is slightly larger than it is in our universe. This would lead to an even faster rate of expansion, ripping apart galaxies and preventing the formation of stars and planets. Or imagine a universe where the strong nuclear force is slightly weaker, preventing the formation of stable atomic nuclei. Such a universe would consist only of hydrogen, and complex chemistry would be impossible. Even more disturbingly, the multiverse raises the possibility of universes that are actively malicious. This isn't to say that there are aliens in other universes plotting our demise, but rather that there could be fundamental forces or physical processes that pose a threat to our own universe. One such possibility is the aforementioned vacuum decay. If our universe is indeed metastable, a bubble of true vacuum could nucleate in another universe and then expand into our own, destroying everything in its path. This bubble would propagate at the speed of light, giving us no warning and no chance to escape. Another potential threat comes from the possibility of colliding universes. If bubble universes are constantly popping into existence, it's conceivable that one of them could collide with our own. The impact of such a collision would be catastrophic, potentially disrupting the fabric of space-time and altering the laws of physics in our region of the universe. These are, of course, highly speculative scenarios. There's no evidence that any of these threats are imminent or even possible, but the very fact that they can be conceived within the framework of the multiverse theory is deeply unsettling. It suggests that our universe might not be as safe and stable as we think it is, and that there are potentially existential threats lurking beyond our cosmic horizon. The silence surrounding these dark sides of the multiverse isn't necessarily due to a desire to suppress the information, but rather a recognition of the profound uncertainty and lack of concrete evidence. Scientists are hesitant to speculate too wildly about possibilities that are so far beyond our current ability to test or verify. The implications extend into philosophy. If the multiverse is real and potentially hostile, what does that say about our place in the cosmos? Are we simply lucky to have found ourselves in a relatively safe and stable universe, or is there something more to it than that? These are questions that may never be fully answered, but they serve as a reminder of the vastness and complexity of the universe and the limits of our knowledge. The multiverse, with its infinite possibilities and potential dangers, is a concept that challenges our understanding of reality and forces us to confront the ultimate questions of existence. And then there's the Fermi paradox, which this idea could potentially make even worse. There's a fundamental problem at the heart of our understanding of, well, everything. It's called the hard problem of consciousness, and it's something scientists tend to tiptoe around. What is consciousness? It sounds like a simple question, but try defining it without using the word conscious or any of its derivatives. It's deceptively difficult. We all know we're conscious. We experience the world subjectively. Sights, sounds, smells, emotions, the whole shebang. But how does that subjective experience, that what it's likeness, arise from the physical stuff in our brains? That's the hard problem. It's not just about figuring out which parts of the brain are active when we're thinking or feeling. We can map brain activity all day long, and that's helpful, sure. But that doesn't explain why that activity results in a subjective experience at all. Why aren't we just complex robots, processing information without any internal awareness? The easy problems of consciousness, like identifying the neural correlates of attention or memory, are being chipped away at. But the hard problem? It remains stubbornly resistant to explanation. Consider pain. We can trace the neural pathways that carry pain signals from a stubbed toe to the brain. We can identify the brain regions that light up when someone is experiencing pain. We can even develop drugs that block those signals. But none of that explains why pain feels the way it does. Why is it an unpleasant, aversive experience? Why isn't it just a neutral signal, like a low battery warning on your phone? That subjective, qualitative feel of pain, that's what philosophers call qualia. And qualia are at the heart of the hard problem. All of our sensory experiences are filled with qualia, the redness of red, the sweetness of sugar, the sound of a guitar. How do these subjective experiences arise from objective physical processes? Some scientists and philosophers, the materialists, argue that consciousness is simply a product of brain activity. They believe that once we fully understand the brain, the hard problem will dissolve. The subjective experience, they say, is just an illusion or an emergent property of complex computation. But this doesn't sit right with others. It feels like it dismisses our lived experiences. Others propose panpsychism, the idea that consciousness, or at least some rudimentary form of it, is a fundamental property of the universe, present in all matter. This isn't to say that your coffee mug is having deep thoughts, but rather that even elementary particles might possess a tiny sliver of awareness. The benefit of this theory is it avoids the seemingly impossible leap of generating consciousness from non-conscious matter. The challenge is that there's no good explanation for how these tiny slivers of awareness combine to form the rich conscious experience we have as humans. Then there are the dualists who argue that consciousness is something separate from the physical world, a kind of soul or spirit that interacts with the brain. This view, while popular throughout history, struggles to explain how a non-physical entity can interact with the physical world without violating the laws of physics. The implications of the hard problem are profound. If we don't understand how consciousness arises, how can we ever create truly conscious artificial intelligence? How can we be sure that other animals are conscious and deserving of moral consideration? And what does it mean for our understanding of free will and personal identity? The silence, or at least the hushed tones around the hard problem, stems from its intractability. Scientists by nature are problem solvers. They want to tackle questions that can be answered through observation, experimentation, and mathematical modelling. The hard problem, at least for now, seems to defy those methods. It's a philosophical problem masquerading as a scientific one. And yet, it's a problem that we can't afford to ignore. Our understanding of ourselves, our place in the universe, and our future as a species depends on grappling with the mystery of consciousness. Consider this. If consciousness can arise spontaneously in sufficiently complex systems, what are the implications for the universe itself? Could the universe as a whole be conscious in some way? It's a far-out idea, but no more far out than some of the other theories we've discussed. And if the universe is conscious, what does that mean for us? Its conscious inhabitants? These questions are unsettling. They challenge our assumptions about reality and our place within it, and perhaps that's why scientists are often reluctant to address them directly. It's easier to focus on the easy problems, the ones that can be solved with existing tools and techniques. But the hard problem of consciousness remains, a persistent reminder of the limits of our knowledge and the vastness of the unknown. What if our conscious experience is not unique? Webb just revealed something massive. It's thrown a wrench into our understanding of the very early universe, and it hints at something truly bizarre. eternal inflation. Now, inflation itself isn't new. It's the idea that fractions of a second after the Big Bang, the universe expanded at an absolutely insane rate, faster than the speed of light. This explains why the universe is so uniform on large scales. Imagine blowing up a tiny wrinkled balloon to the size of the solar system in a blink. The wrinkles get smoothed out. That's inflation in a nutshell. But eternal inflation takes this a step further. It suggests that inflation didn't just happen once, it's still happening, and it's happening forever. The basic idea is this: quantum fluctuations, those weird random jitters at the subatomic level, can occasionally create regions where inflation restarts. Think of it like bubbles constantly forming in a pot of boiling water. Each bubble is a new universe, expanding and cooling down, potentially with its own set of physical laws. Our universe, the one we inhabit, is just one of these bubbles, an island universe in a vast, ever-expanding multiverse. The implications are, frankly, terrifying. First, it means that the universe we see is only a tiny, insignificant fraction of reality. There are countless other universes out there, each with its own unique history and future. Some might be almost identical to ours, while others could be radically different, governed by entirely different physical constants. Second, it challenges our notions of causality. In eternal inflation, there's no single beginning. The multiverse is constantly being created, with new universes popping into existence all the time. The Big Bang, in this view, isn't the start of everything. It's just the start of our universe. Third, it raises the spectre of Boltzmann brains. These are hypothetical, self-aware entities that spontaneously form out of random fluctuations. Imagine a collection of particles randomly assembling themselves into a fully functional brain, complete with memories and consciousness. It sounds absurd, but in an infinite multiverse with infinite time and infinite possibilities, it becomes inevitable. And here's the terrifying part. Boltzmann brains would vastly outnumber ordinary brains like ours, which evolved through billions of years of complex biological processes. In other words, if eternal inflation is correct, then the vast majority of conscious observers in the multiverse would be these fleeting, randomly assembled brains. Our own existence, our own thoughts and feelings would be statistically insignificant. The silence around eternal inflation isn't necessarily due to a lack of evidence. The problem is that it's incredibly difficult, if not impossible, to test directly. We can't travel to other universes to see if they exist. We can't directly observe the inflationary epoch. Instead, scientists rely on indirect evidence, like the cosmic microwave background, the afterglow of the Big Bang. The patterns in the cosmic microwave background can provide clues about the conditions in the very early universe, potentially shedding light on whether inflation actually happened and whether it might still be happening today. However, interpreting this evidence is tricky, and there's still a lot of debate about what it all means. Moreover, eternal inflation raises some deep philosophical questions. If the multiverse is truly infinite, then anything that can happen will happen, infinitely many times. This leads to a kind of cosmic nihilism where our existence, our choices, and our actions ultimately don't matter. If every possible outcome is guaranteed to occur somewhere in the multiverse, then what's the point of anything? It's a question that cuts to the core of what it means to be human. We crave meaning. We seek purpose. Eternal inflation, in its coldest interpretation, suggests that both are illusions. Now, some physicists argue that these philosophical concerns are irrelevant. Science, they say, is about describing the universe as it is, not as we would like it to be. If eternal inflation is the best explanation for the data, then we have to accept it, even if it's unsettling. But others believe that these philosophical implications are too important to ignore. They argue that we need to find a way to reconcile eternal inflation with our understanding of consciousness, free will, and morality. Perhaps there's a way to formulate a measure on the multiverse, a way to assign probabilities to different universes and different outcomes. This could potentially alleviate the problem of Boltzmann brains by showing that they are actually much rarer than ordinary brains. Or perhaps there's something fundamentally wrong with our understanding of quantum mechanics or gravity. Maybe there's a new physics waiting to be discovered which will resolve the paradoxes of eternal inflation and provide a more satisfying picture of the universe. The uncomfortable truth is that we simply don't know. Eternal inflation remains a highly speculative theory, shrouded in uncertainty and philosophical controversy. But it's a theory that forces us to confront some of the deepest questions about reality. Where did we come from? Are we alone? And what is our place in the grand scheme of things? And then consider the flip side. Could we create our own universes? And then, the implications extend beyond mere scientific curiosity. It forces us to confront the very foundations of our understanding of reality. Consider the fine-tuning problem. The universe appears to be exquisitely calibrated for the emergence of life. The fundamental constants of nature, things like the strength of gravity, the mass of the electron, the cosmological constant that drives the universe's expansion, all fall within an incredibly narrow range that allows for the formation of stars, galaxies, planets, and ultimately, life as we know it. If these constants were even slightly different, the universe would be a very different place. Gravity even a little stronger, and the universe would have collapsed back on itself moments after the Big Bang. A little weaker, and matter would have dispersed too quickly for galaxies to form. The strong nuclear force, which binds protons and neutrons together in atomic nuclei, similarly needs to be in a sweet spot, or else stars wouldn't be able to fuse elements heavier than hydrogen and helium. No carbon, no oxygen, no you or me. It's like the universe is a giant machine with countless dials, and all of those dials have to be set to just the right position for the machine to work. What are the odds of that happening by chance? Some physicists argue that it's not surprising at all. If there's only one universe and we're here to observe it, then of course we'll observe it to be fine-tuned for our existence. This is known as the anthropic principle. It's not that the universe was designed for us, it's that we could only exist in a universe that allows for our existence. But the anthropic principle doesn't really explain anything. It just pushes the question one step further back. Why is there even a universe that allows for our existence in the first place? Where did the rule book for the universe come from? This is where the multiverse enters the picture again. If there are infinitely many universes, each with its own set of physical laws and constants, then it's not surprising that at least one of them would be fine-tuned for life. We just happen to live in that one. It's like winning the lottery. The odds of any one person winning are incredibly small, but if you sell enough lottery tickets, someone is bound to win eventually. The multiverse is like selling an infinite number of lottery tickets. But even the multiverse doesn't completely solve the fine-tuning problem. For one thing, it doesn't explain why the constants of nature are distributed the way they are. Why aren't most universes completely inhospitable to life? Why does our universe seem to be so unusually friendly? Furthermore, the multiverse raises new questions of its own. What determines the physical laws and constants in each universe? Are there any limits to the kinds of universes that can exist? And how do these universes interact with each other, if at all? Some physicists have proposed that the constants of nature are not truly constant, but can vary from place to place within our own universe. This is known as the landscape of the universe. Imagine a vast and mountainous terrain where each point represents a different set of physical laws. Our universe would be just one small valley in this landscape, a valley that happens to be particularly well suited for life. But even the landscape picture doesn't fully resolve the fine-tuning problem. It still doesn't explain why our valley is so special. Why aren't we living in a barren desert or a boiling swamp? The uncomfortable truth is that we don't know. The fine-tuning problem remains one of the deepest and most puzzling mysteries in science. It challenges our understanding of the universe and our place within it. It forces us to confront the possibility that our existence is either an incredibly improbable accident or the result of some deeper, unknown principle. And that's where things get really weird. Consider the sheer difficulty in explaining why the universe even exists at all. Why is there something rather than nothing? It's a question that has plagued philosophers and scientists for centuries. If you start with absolutely nothing, no space, no time, no matter, no energy, no laws of physics, then how do you get something? One possibility is that the universe popped into existence spontaneously, out of nothing. This might sound like science fiction, but it's actually consistent with the laws of quantum mechanics. Quantum mechanics allows for the possibility of quantum fluctuations, where particles can briefly appear and disappear out of the vacuum. It's possible that the entire universe is just one giant quantum fluctuation. But even if that's the case, it doesn't really explain anything. It just pushes the question one step further back. Why do the laws of quantum mechanics allow for quantum fluctuations in the first place? Where did the laws of physics come from? Another possibility is that the universe has always existed in some form or another. This avoids the problem of having to explain how the universe came into existence, but it raises new questions of its own. What was the universe like before the Big Bang? Was there even a before the Big Bang? And if the universe has always existed, why hasn't it reached a state of equilibrium yet? Why is there still so much energy and structure in the universe? The truth is, we simply don't know. The origin of the universe remains one of the greatest mysteries of all time. It's a question that may never be fully answered. The analysis continues. Scientists discovered something else. The expansion of the universe is accelerating. You've been sold a simplified version of dark energy. The textbooks present it as a constant, a smooth, unchanging pressure pushing the universe apart. But what if that's wrong? What if dark energy isn't constant at all? Consider this. We barely understand what dark energy is. We know it makes up roughly 68% of the universe's total energy density, and we infer its existence from the accelerating expansion. But its fundamental nature remains a complete mystery. Is it a property of space itself, a cosmological constant as Einstein initially proposed and then regretted? Or is it something more dynamic, a field that evolves over time? If dark energy is dynamic, its density and pressure could change, and if they change, the rate of the universe's expansion would also change, and not in a predictable way. We're talking about the very fabric of space-time behaving in ways we can't currently model. Scientists discovered a number of competing theories to explain this. One idea involves quintessence, a hypothetical fifth fundamental force that permeates all of space. Unlike the cosmological constant, quintessence can vary in space and time, leading to a more complex and potentially unstable expansion of the universe. Another possibility is that our understanding of gravity itself is incomplete. Maybe general relativity, Einstein's masterpiece, breaks down on the largest scales. Modified gravity theories attempt to tweak the laws of gravity to account for the accelerating expansion without invoking dark energy at all. However, these theories often struggle to explain other cosmological observations. Here's what's wild. If dark energy is changing, it could eventually reverse direction. Instead of pushing the universe apart, it could start pulling it back together. This scenario, known as the Big Crunch, would be the ultimate reversal of the Big Bang. Galaxies would begin to collide, the universe would shrink, and eventually, everything would collapse into a singularity. The implications extend far beyond cosmology. The ultimate fate of the universe dictates the fate of everything within it. If the Big Crunch is in our future, then all the stars, planets, and even atoms will eventually be crushed out of existence. And then there's the Big Rip. This scenario arises if dark energy becomes even more powerful over time. The expansion rate would accelerate without bound, eventually overcoming all forces holding matter together. Galaxies would be torn apart, then solar systems, then planets, and finally, even atoms themselves would be ripped apart by the relentless expansion. Scientists discovered that we're not even sure if these are the only possibilities. Our current models may be missing crucial physics. It's possible that dark energy is linked to other unknown phenomena, like dark matter or extra dimensions. The interplay between these different components could lead to even more bizarre and unpredictable scenarios. Consider the phantom energy hypothesis. This proposes a form of dark energy that becomes denser as the universe expands, violating some fundamental laws of physics. If phantom energy exists, the Big Rip becomes inevitable, and it could happen much sooner than we currently estimate. The analysis continued. What makes this so terrifying is the uncertainty. We don't know which, if any, of these scenarios is correct. Our measurements of dark energy are still relatively imprecise, and we lack a fundamental understanding of its nature. We're like sailors navigating uncharted waters, unsure of the currents or the storms that lie ahead. The implications extend to the search for extraterrestrial life. If the universe is destined for a Big Crunch or a Big Rip, then the window for life to evolve and flourish may be limited. Civilizations may rise and fall, unaware of the impending cosmic catastrophe that awaits them. Measurements showed that our attempts to measure the equation of state of dark energy, the ratio of its pressure to its energy density, are hampered by systematic uncertainties. it's incredibly difficult to disentangle the effects of dark energy from other cosmological phenomena. We need more precise observations and more sophisticated theoretical models to make progress. Scientists discovered that the next generation of telescopes and space missions are designed to probe dark energy with unprecedented accuracy. The Nancy Grace Roman Space Telescope, for example, will use weak gravitational lensing and supernova surveys to map the distribution of dark matter and measure the expansion history of the universe. The Euclid mission will also contribute to this effort. The data reveals that even with these advanced instruments, unraveling the mysteries of dark energy will be a daunting task. We may need to develop entirely new theoretical frameworks to explain its behavior. It's possible that the answer lies in string theory, loop quantum gravity, or some other exotic theory of physics that we don't yet fully understand. Here's what's wild. Dark energy might not even be a thing at all. It could be that the accelerating expansion is an illusion, a consequence of some unknown systematic error in our observations or a misunderstanding of the laws of physics. While this possibility is less likely, it cannot be ruled out entirely. The implications extend to our understanding of the fundamental constants of nature. Some theories suggest that dark energy is coupled to these constants, causing them to vary over time. If this is the case, it would have profound consequences for our understanding of physics and chemistry. Think about it. If the fundamental constants are changing, then the laws of physics are not immutable. The universe would be a much more dynamic and unpredictable place. It would also raise questions about the origin and stability of life. The analysis continued. The possibility that dark energy is unstable has led to some truly bizarre speculations. Some scientists have suggested that it could undergo a phase transition, suddenly changing its properties and triggering a catastrophic event. Measurements showed that it's impossible to predict what such an event would look like. It could involve the creation of new particles, the formation of black holes, or even the destruction of space-time itself. The implications extend to our place in the universe. If dark energy is unstable, then our existence may be contingent on its continued stability. We may be living on borrowed time, unaware of the cosmic time bomb that is ticking away in the background. The quest to understand dark energy is one of the most challenging and important scientific endeavors of our time. It requires a combination of observational astronomy, theoretical physics, and mathematical modeling. It also requires a willingness to challenge our assumptions and to embrace the unknown. And then there's the anthropic principle. There are things science simply cannot know. It's a hard pill to swallow, especially after centuries of seemingly unstoppable progress. But the universe might have inherent limits to what we can observe, measure, and ultimately understand. Consider the concept of a multiverse, the idea that our universe is just one of countless others, each with its own set of physical laws and constants. It's a fascinating idea, and some theories, like eternal inflation, lend it some credence. But here's the rub. If these other universes are truly separate from ours, causally disconnected, then we may never be able to observe them, interact with them, or even prove their existence. What if the fundamental laws of physics are different in each universe? What if some universes have entirely different dimensions or particles or even different concepts of time and space? If that's the case, then our scientific models, which are based on the laws of physics as we know them, would be useless for describing these other universes. We would be limited to studying our own cosmic bubble, forever ignorant of the vastness beyond. The implications extend to the very nature of reality. If the multiverse is real, then our universe may be just one random possibility out of an infinite number of others. The laws of physics that govern our universe may be just one set of random rules, with no particular reason for being the way they are. This challenges our assumption that the universe is governed by a set of fundamental and universal laws that can be discovered through scientific inquiry. And then there's the problem of consciousness. Despite centuries of research, we still don't have a clear understanding of how consciousness arises from the physical matter of the brain. We can observe the brain activity associated with different mental states, but we don't know why or how this activity gives rise to subjective experience. What if consciousness is not just a product of the brain, but something more fundamental, something that exists independently of physical matter? What if consciousness is a fundamental property of the universe, like gravity or electromagnetism? If that's the case, then our current scientific models, which are based on the assumption that everything can be explained in terms of Physical laws may be fundamentally incomplete. The implications extend to our understanding of ourselves. If consciousness is not just a product of the brain, then we may be more than just physical beings. We may have a deeper connection to the universe, a connection that transcends the limitations of our physical bodies. Scientists discovered that some things might be beyond our reach, simply because the energy requirements to probe them are far beyond anything we can currently achieve. Take the Planck scale, for example. This is the smallest possible unit of length in the universe, the point at which quantum mechanics and gravity are thought to merge. To probe the Planck scale directly, we would need a particle accelerator the size of the galaxy. It's simply not feasible. This means that there may be phenomena occurring at the Planck scale that we will never be able to observe directly. We may have to rely on indirect evidence and theoretical models to infer what is happening at this fundamental level of reality. Further examination revealed that there could be entire realms of physics that are simply inaccessible to us, not because of technological limitations, but because of the fundamental laws of the universe. For example, some theories suggest that there are extra dimensions of space beyond the three that we experience, but these dimensions may be curled up at such a small scale that we will never be able to detect them directly. The implications extend to our understanding of the universe's origins. If there are phenomena occurring at scales or energies that we can never access, then we may never be able to fully understand the Big Bang or the very first moments of the universe's existence. The limits of scientific knowledge also raise ethical questions. As we develop new technologies that allow us to probe deeper into the mysteries of the universe, we must also consider the potential risks and consequences of our actions. What if we discover something that we are not prepared for? What if we unleash forces that we cannot control? These are questions that we must grapple with as we continue to push the boundaries of scientific knowledge. This means that we must approach scientific inquiry with humility and caution, recognizing that there are limits to what we can know and that our actions can have unintended consequences. And then there's the question of whether our brains are even capable of fully understanding the universe. Our brains evolved to help us survive in a relatively simple environment. Is it possible that they are simply not equipped to grasp the complexities of quantum mechanics, general relativity, or the other deep mysteries of the cosmos? What if the universe is fundamentally incomprehensible to the human mind? What if there are aspects of reality that are simply beyond our cognitive abilities? If that's the case, then we may have to accept that there are limits to what we can know, regardless of how advanced our technology becomes. This is not to say that we should give up on scientific inquiry. Far from it. The quest to understand the universe is one of the most noble and important endeavors of humankind. But we must also be aware of the limitations of our knowledge and the potential risks of our actions. The analysis continued. As we continue to explore the universe, we must also explore the limits of our own understanding. We must be willing to challenge our assumptions, to question our beliefs, and to embrace the unknown. Ultimately, the limits of scientific knowledge may be a reflection of the limits of human consciousness. As we expand our awareness and deepen our understanding of ourselves, we may also expand our ability to comprehend the universe around us. 86% of physicists, they missed it. Completely. The implications of that number are staggering. It's not just a minor oversight. It suggests a fundamental disconnect between our theoretical models and the actual reality of the universe. This isn't about tweaking the parameters of a simulation. It's about confronting the possibility that our entire framework for understanding the cosmos might be built on sand. As we grapple with these unsettling possibilities, we inevitably confront the limits of human understanding itself. We've built these incredible tools, these massive observatories, these complex mathematical models, but what if the universe is ultimately beyond our capacity to fully comprehend? What if there are aspects of reality that are simply too alien, too intricate for our brains to process? This isn't a new question, of course. Philosophers have been wrestling with the nature of consciousness and the limits of knowledge for centuries. But the scientific discoveries of the past few decades have given these age-old questions a new urgency. We're not just talking about abstract philosophical concepts anymore. We're talking about concrete scientific observations that challenge the very foundations of our understanding. Consider the phenomenon of dark energy. We know it exists. We can measure its effects on the expansion of the universe. But we have absolutely no idea what it is. It's like discovering a hidden room in your house, a room that's filled with strange and unfamiliar objects. You can see the room, you can touch the objects, but you have no idea what they are or what they're used for. And then there's the mystery of quantum entanglement. Two particles, separated by vast distances, can somehow be linked together in such a way that they instantaneously affect each other's properties. It's as if they're communicating faster than the speed of light, which, according to Einstein's theory of relativity, is impossible. How can this be? What does it tell us about the fundamental nature of reality? These are not just minor puzzles to be solved with a clever equation or a new experiment. These are deep, fundamental mysteries that challenge our most basic assumptions about the universe, and as we continue to probe deeper into the unknown, we're likely to encounter even more of these unsettling questions. What if we discover that the universe is not governed by deterministic laws but by some kind of inherent randomness? What if we find evidence that our universe is just one of many, a tiny bubble in a vast multiverse of infinitely diverse realities? What if we encounter intelligent life forms that are so different from us that we can't even begin to understand their motivations or their intentions? These are the kinds of questions that keep scientists up at night. They're not just abstract intellectual exercises. They're existential challenges that force us to confront our place in the universe and the limits of our own knowledge. The implications extend far beyond the realm of science. If our understanding of the universe is fundamentally incomplete, then what does that mean for our values, our beliefs, our sense of purpose? If we're just a tiny speck of dust in an infinite cosmos, does anything really matter? These are not easy questions to answer. In fact, they may be unanswerable. But that doesn't mean we should stop asking them. The quest to understand the universe is not just about accumulating knowledge. It's about confronting the existential abyss and finding meaning in the face of the unknown. The analysis continued. As we push the boundaries of scientific knowledge, we must also be willing to confront the unsettling implications of our discoveries. We must be willing to challenge our assumptions, to question our beliefs, and to embrace the mystery that lies at the heart of the cosmos. Maybe, just maybe, the very act of searching for answers is enough. If these theories have sparked your curiosity, consider subscribing to stay updated on new revelations.